Hi, my name is Thomas Carr, and I'm a graduate student in mathematics at the University of Washington. And this is going to be a set of online video lectures on differential equations. So the structure is going to be pretty standard for a first course in differential equations. There are going to be three main parts. So first, we're going to talk about first order ordinary differential equations, or ODEs for short. Then we're going to talk about second order linear differential equations. And finally, we're going to talk about Laplace transforms. In particular, how we can use Laplace transforms to solve ordinary differential equations. Okay, so the main prerequisite for this course is just going to be a single variable calculus course. So single variable calculus. So no multivariable calculus is going to be necessary. But it is going to be important that you've seen both differential and integral calculus. So differential and integral. And I mean, you might think differential equations, that's just going to involve derivatives, but it turns out that a lot of the solution methods are going to involve integrals in one way or another. One last thing, so along the way, I'm going to be providing some short problems, sort of interspersed in these lectures. And for the maximum benefit, what you should really do is pause the lecture and try to work through these problems along the way. They're designed to not be too difficult and basically just reinforce the concepts of the lecture. Okay. So let's go ahead and say what a differential equation is. So definition. A differential equation or DE for short. So what is it? It's an equation, mathematical equation, that relates one or more functions and their derivatives. Okay. So these equations are actually not going to be like the equations you've seen in algebra. In algebra, you're often solving for the value of a certain variable. For example, you might find that x equals 27. So you're solving for a number, actually. Differential equations, they're not like that. So a solution to a differential equation, it's not a number, it's a function, actually. So a function, or even a collection of functions. And these functions are going to satisfy the equation. So we're looking for a collection of functions that satisfy the equation. So let's see what these differential equations look like. So I'll just write a few examples, just so we get an idea. So the first one we'll look at is y prime minus y squared equals 1. Okay, so what's going on here? So I want you to keep in mind that this y here is actually a function. So it's not a number, it's a function. And so I often like to think of differential equations as sort of mathematical riddles. So this one is saying if you take the derivative of a function and you subtract the square of that function, then you get the constant function 1. Okay, so that's the differential equation, and we're solving for the function y that satisfies this relationship. And if you'd like, you can try to think about what this function is. If you'd like a hint, you should think about trigonometric functions that might satisfy this. And we'll talk soon enough about how to solve this methodically. But that's an example of a differential equation. Let's write down another example. So this one will have I double prime of t, so second derivative, plus r over L times I prime of t, first derivative, plus 1 over LC times I of t equals 0. And this differential equation actually comes from electrical engineering. So this is the equation for an RLC circuit, an RLC series circuit in particular. And here R, L, and C are constants, and they just depend on the circuit. And I right here is the current function. So this describes the current in the circuit at any time. And this differential equation gives a relationship between the current, its first derivative, and its second derivative. And we're going to solve this differential equation in the second part of the course. Okay, let me give you an example of a differential equation that we will not solve in this course. So this one is the partial derivative of u with respect to t equals alpha, a constant, times the second partial derivative of u with respect to x. And this is a famous differential equation. This is called the heat equation. So this is a one-dimensional heat equation. And the reason we're not going to solve this one in this class is because this is an example of a partial differential equation. So this is a partial differential equation, or PDE for short. Partial differential equation. Partial differential equations are very important and very interesting, but in this course we're only going to solve ordinary differential equations. So that's what this O stands for up here, ordinary, as opposed to partial. So we only have ordinary derivatives, no partial derivatives. Okay. All right, so equally as important as this mathematical definition of what a differential equation is how we're going to be talking about how differential equations arise in the real world. So how do differential equations arise? Where do they come from? And we're going to spend the rest of this lecture talking about that. So let's just quickly recall. So let's say we have a function of time, okay? So f is just some function that varies in time. Well, what is the meaning of the derivative, f prime of t? Well, you might remember from calculus that this has the meaning of the instantaneous rate of change. Okay. So basically any time we have a natural or physical process that's going to involve instantaneous rates of change, or some kind of change in time, there's probably a differential equation that we can write down. And so that's a common theme that we're going to see in this course. So let's look at a few examples of this. So example 1, let's look at the growth of a bamboo plant. So bamboo plant grows at a rate of a certain fixed number of centimeters a day. So k centimeters per day. Okay. And what we want to understand here is the height of the plant at any time, h of t. So h of t will represent the height in centimeters, let's say, at time t. Right? And t is measured in days. Okay. So what is this saying? It's saying that the height is changing at a rate of k centimeters per day. So the rate of change of the height, dh dt, derivative of h with respect to t, is, what is it? It's just this fixed number k. So dh dt equals k. And that's actually a differential equation that we just wrote down. This is actually a fairly simple differential equation. This is one that we can solve actually just with techniques from single variable calculus. So recall, what is the solution? It's this function h of t, and we can just write down what h of t is. It's going to be kt plus c, right? If the derivative is k, then the function itself is going to be kt plus some arbitrary constant. Okay. Let's just sketch a graph of what this is going to look like. So we'll graph the solution. Actually, it's more than one solution, right? So we actually just wrote down infinitely many functions here. The c can be any number. Okay, so this will be the t-axis, and this will be the h-axis. And a solution might look like this, right? So we just get linear equations here, and the slope is going to be k. So the slope is k. And what is this number here? Well, you'll notice that. So note that that when we plug in 0, h of 0 is just going to be c. Which means that c is actually going to have the meaning of the initial height in this case. So that's the initial height. So this is that c right here. I'll call it h0 to mean the initial height. Okay. Great. So we just solved our first differential equation. And this is one where we didn't need any new techniques. We could just find the answer by taking an antiderivative, right? Because we're given that the derivative is k, so of this unknown function h, so the function h is going to be kt plus c. Okay, so I want to look at a more interesting example now. So let's move this up. So this will be example 2. And this example, I want to consider a rabbit population. So a rabbit population. And a rabbit population is going to grow. So it grows at a rate proportional to the population size. Okay, so let's just think about this to make sure this makes sense. So if we only have a few rabbits, then only a few of these rabbits are going to be reproducing, and we're only going to be adding a few new rabbits to the population every year. Whereas if we have a lot of rabbits, a lot of them are going to be reproducing, we're going to be adding many more rabbits every year. So this makes a lot of sense. And here we want to understand R of t, let's call it. So R of t is the number of rabbits at time t. And to write down a differential equation, we just ask ourselves, what is dr dt? So how is r changing with time? How is the number of rabbits changing with time? Well, we just deduce that it's changing at a rate proportional to the population size. So in other words, dr dt is k times the population size. So k times means proportional to, right? It's a constant times the population size. So here k is called the constant of proportionality. And r is the same as that r over there. It's this unknown function r of t that we're trying to solve for, right? So this is a more interesting differential equation because we can't just solve this one by taking an antiderivative. So make sure you can appreciate that. If we try to take an antiderivative, we get r equals k times, well, the antiderivative of r, but we don't know what r is. That's what we're trying to figure out, right? We're trying to solve this for r of t. So we're going to talk about how to solve this one soon enough. I don't want to solve it today, but I just want to introduce another concept. So suppose I actually tell you a solution. So suppose I tell you that r of t equals e to the kt is a solution. Okay, so suppose I hand you a solution. How can you check, right? So how can you check to see if it's actually a solution? And this is fairly simple. So we have r of t is e to the kt. All we have to do is plug this into the differential equation. So just like in algebra, you can plug in a solution to check. So notice that in order to check, we're going to have to actually plug something in on this side too, dr dt, which is, well, what is it? It's the derivative of e to the kt, which is ke to the kt by the chain rule. Okay. And then if we plug this in, so on the left side, we just get k times e to the kt. And on the right side, we get k, right, times this r. But that's e to the kt. And we see that we have the same thing on both sides, so it checks out. Right, we have the same function on both sides. Remember with differential equations, these are functions, right? So we need equality of functions. They have to be the same function. They can't just take the same value at a particular value of t. Like, they really have to be the same function. Great. So that is a solution. And I'll just say it turns out. So it turns out all the solutions look like this one. So in particular, they have the form, not y, sorry. R of t equals a times e to the kt, where a is any constant. Okay, so this is any number. Okay. I want to do another example, but before I do, I'll just give you a quick problem to try. So here's a problem. This is just going to be practice verifying the solution to a differential equation. So problem is to verify that y of t equals e to the negative t squared is a solution to this differential equation. So this differential equation is going to be y prime equals -2 times t times y. Okay. So you're going to check that this is a solution. In order to check, you're going to have to take the derivative of this, plug it in there, verify that you get the same function. So again, you'll have to use the chain rule. Okay, so let's look at a third example. So this is going to be an example from chemistry. So we're going to look at radioactive decay, in particular radiocarbon dating. Which is a very important application. Okay, so first let me just tell you about how radiocarbon dating works. So basically, anytime a living organism dies, it has a certain amount of carbon-12, so that'll be the blue. So this will be carbon-12. Okay. It has mostly carbon-12, but it also has a small amount of a different isotope of carbon called carbon-14. Okay. And essentially, after an organism dies, the carbon-12 will stay carbon-12. The carbon-14 will begin to decay, and it'll actually decay to, I believe, nitrogen. So it'll undergo a beta decay to end up at nitrogen-14. So this will go to this. And essentially, at any time, there's a fixed probability of any one carbon-14 atom decaying into nitrogen-14. So it's a probabilistic process. And if you think about it, if there's a lot of carbon-14, then there are more opportunities for one of these carbon-14 atoms to decay. And so we find that the decay rate of carbon-14 is going to be proportional to the amount of carbon-14. So it's proportional to the amount of carbon-14. Okay. And the idea is this process can essentially be used to estimate the age of an organic material based on the proportion of carbon-12 to carbon-14. Okay, so let's write down a differential equation. In fact, we just did in words. This is a differential equation right here. But let's translate it to math. So what's our function going to be? So we'll just call it y of t this time. And this is going to be the amount of carbon-14, let's say after t years. Okay, and how is it changing? Okay. Well, first of all, it's decreasing. So that means, well, what does that mean about dy dt? And if a function is decreasing, then its derivative is going to be negative. So we need a negative sign here. And it's proportional to, meaning k times, the amount of carbon-14. What's the amount of carbon-14? That's the function y itself. So if dy dt equals negative ky, and that's going to be the differential equation for radioactive decay. We could have actually left out the minus sign and just said k is going to be a negative number also. But I'm going to try to follow the scientific convention that these constants are always going to be positive. So k is a positive constant, and so I need this minus sign. And you might notice this looks just like the rabbit example, except without the minus sign. So this is another common theme that we're going to see, is that often seemingly different problems are going to result in the same differential equation. In fact, this differential equation, I mean, it can literally model hundreds of different physical problems. Okay. So I'll just bring up one more point in the context of this problem. So suppose we fix a value of k. I just want to reason about this differential equation. So suppose k equals, let's say, 0.01. Okay. What does this mean? So what does it mean for dy dt to equal negative 0.01 times y? So this means that the instantaneous rate of change in the carbon-14 amount is a 1% decrease every year. It's around 1% decrease. Every year, okay? What this does not mean, okay, is that, let's say we had 200 grams of carbon-14. So what this does not mean is that we're going to lose 2 grams in that year. Okay? That's an overall rate of change. It means at that very moment, it's decreasing at that rate, right? That of 2 grams per year. But keep in mind, one day from now, we're going to have less than 200 grams. And now we're going to be calculating this whole thing again, right? So we need to take 1% of that. And so we have to just always keep in mind that it's going to be an instantaneous rate of change that this differential equation is representing. It's not an overall rate of change, it's an instantaneous rate of change. So this does not necessarily mean that we're going to have 198 grams at the end of the year. That might be a pretty good estimate though, but just keep in mind that we're always dealing with instantaneous rates of change. Okay. I think we're almost done. Let's do one more example because those last two examples are basically the same example. Let's do a different one. So here's example 4, I guess we're on. And this will be an example from physics. So this will be Hooke's law. Okay. Hooke's law has to do with springs. So let's draw what we're talking about here. Okay. So we have a spring attached to the wall. And then we're going to attach a block. Let's suppose there's no friction here for now. So we just have a block attached to a spring, and it can bounce back and forth. And let's say this is a block of mass m, measured in grams. And so what we want to understand is the position of this block at any given time. So let's say we've actually stretched it out a little bit. So let's say x equals 0 is going to be right here, and that'll be the equilibrium position. We'll say this direction is positive, and this direction is negative. And the current position of the block is, we'll just call it x0. Okay. And so x of t is what we want to understand, and that's going to be the position of the block relative to equilibrium. Relative to the equilibrium position. Okay. So what does Hooke's law say? So Hooke's law is actually an example of a force law in physics. So it's going to tell us what the force exerted by the spring is. So what Hooke's law says is that the force exerted by the spring has a magnitude that's proportional to the displacement. Okay, so I won't write that in words. I'll just write it. I'll write it down in mathematical language. So again, the force is proportional in magnitude, so k times to the displacement. And what is the displacement? That's x of t. So let's write down x. But again, we're understanding that x actually is a function, x of t. Oh, and I forgot to say one thing. It acts in the opposite direction. So we're going to have a minus sign. So the spring force is negative k times the displacement. Okay. This makes a lot of sense because if we pull out the spring, the force is going to be acting in this direction. It's going to want to return back to its natural position. And if we push in the spring this way, if we have the block all the way over here, then the spring is going to want to push it back out. So it's in the opposite direction as the displacement. Okay. This is going to turn into a differential equation, actually. And that's because by Newton's second law, any force is going to induce an acceleration. So F equals ma. It's Newton's second law. At least this is a version of Newton's second law when the mass is constant. So the mass is constant here. So F equals ma. But what is A? A is the second derivative of position, if you recall from calculus. So it's the second derivative of x. So if we put this all together, we have ma. What is ma? It's m times this, right? So it's m times the second derivative of x with respect to t. And that equals the force. So the only force that's acting on this system, we're assuming, is the spring force. So this is actually going to equal negative k times x. And there we have a differential equation. This should be t squared. So this is the Hooke's law differential equation. And this is actually an example of a second order differential equation. So this is a second order differential equation. That's because the second derivative appears. So order has to do with the derivative. So let's just define that. That word is going to come up a lot. So definition. How should I say this? So a differential equation has order n if the highest derivative appearing is an nth derivative. Okay. Let's just quickly jot down a few examples. So dy dt equals y cubed plus t squared. Notice we have both the dependent variable y and the independent variable t appearing here. Y is a function of t, right? So we're taking a derivative of y with respect to t. What is the order of this differential equation? So if you said first order, then you're right. Hopefully you weren't fooled by this 2 or the 3 up there, right? The order is just the highest derivative that's appearing. So here we have a first derivative, so it's first order. Let's look at this example. Y triple prime minus y prime equals 4 times y. Well, that's the third order. It's the highest derivative appearing as a third derivative. Okay, great. So I think that's about a good length for this first lecture. I want to leave you with one problem though. So here's a problem that you should try. So again, I'm going to tell you what one solution is to this Hooke's law differential equation. So I'll say one possible solution to the Hooke's law differential equation is x of t equals cosine of alpha t. Okay. For some alpha, so for a particular value of alpha. And what I want you to do is find what this alpha is. So find alpha in terms of the constants in the equation. So in terms of, what are the constants? K and M. So you should get a formula involving K and M for this alpha. And just to kind of get you started, the way you'd start out is, notice that we need to plug in a second derivative of x. So here's what x is. Take its second derivative, and then you'll plug it in, and then you'll keep in mind that we want to get the same function on both sides. And so if you write that down and then stare at it for a bit, you'll be able to deduce what alpha has to be in order to get the same exact function on both sides. So definitely try that problem, and I'll see you next time.